Test, test. Anybody on Zoom? We're just checking the audio is working.
Can you hear me? Yeah, I can hear you.
Okay, perfect. Awesome. Sounds great. Thank you. All right, let's get started. So I just want to start off by thanking everybody who's here virtually and in person. This is our first annual PDR. Our team has worked a lot this semester on our physical design within our electrical software and aeromechanical teams, and we're really excited to present some of this work and appreciate all of your time. So quick team overview for those of you who aren't familiar with our organization, just to kind of give a bit of a background. So right now our team sits at around 75 members, mostly within the engineering department, aerospace engineering, computer engineering, computer science, ECE, those kinds of domains. This is actually our 25th year as an organization, although we kind of have rebounded in the last 2 years and jumped from about 10 to 15 members up to 75. So we're seeing some really good progress, and we'll showcase some of that here in the PDR. So a bit of a brief overview. What is the goal of our organization? So the end goal is to participate in this AUVSI competition that occurs every single year in Maryland. So our organization develops, from the ground up every single year, an unmanned aircraft. So it's going to be, a UAV. Usually it's a fixed wing aircraft. And then we also develop data transmission systems and computer vision systems to go along with that. So quick overview, if you start here at step 1, we have to take off autonomously. We then move into our Waypoint Navigation part of the competition, in which we have, we're given GPS coordinates, which are essentially, bounding areas that we're not allowed to fly through. So we have to use route planning to make sure that we're able to, avoid those areas. We then move into our UGV drop part of the competition, where we drop a 1 kilogram kind of dummy or like a car essentially to a certain GPS coordinate. And then we will move into our final part of the competition, which is Nathan. And then we move into the most technical probably part of the competition, which is this computer vision aspect. And here we're given 1 to 2 foot targets on the ground. And while moving 40 miles an hour at 200 feet in the air, we have to kind of detail some of the characteristics of those targets. And then finally, those are transmitted back to the ground. And the kind of goal of this is to all be done autonomously. So, like I said, we really have 3 main parts to our team. We have the aeromechanical team. That's the ones that are, really the heart and soul of the team. They're going to be building the aircraft. They're going to be doing all the manufacturing work, but they're going to be working very closely with electrical and software as well to kind of fulfill those requirements. So while we do go through this presentation, keep in mind that, a lot of these requirements are drawn from other sub-teams. So we need to kind of contextualize that within the project. Here's kind of another picture that outlines how the competition will work more specifically. So these waypoints are what we would need to fly. These yellow zones are no-fly zones. And then this blue shaded area over here is where we might have to complete our searching or computer vision task. So I'll hand it off to Eric, who is our aeromechanical lead, to run you through some of the design decisions and kind of our design that we're planning to go for this year. And the way that this is going to work, or that we envisioned it, is we have about 45 minutes built in for the aeromechanical presentation. And we really want this to be kind of conversational kind of interactions. So whenever you feel that you have an interjection or a critique, please feel free to jump in during the presentation. We will reserve 5 to 10 minutes at the end, but we'd like this to be as back and forth as possible and address problems as they come up. So I'll hand it off to Eric, and he'll run you through the aeromechanical.
All right, hello everybody. My name is Eric O'Keefe. I'm a junior here at Purdue studying mechanical engineering. I've been leading up the aeromech team this semester. We've made lots of good progress, lots of design progress, and we're finally getting into our manufacturing stage where we can actually build it and test it. So we're going to see if our designs are going to pay off in the end here. But we're very thankful for everybody that is able to come today and help give us feedback so that we can make changes, optimize our design, and then go ahead and move forward and do very well at the competition this year. So our team structure for the aeromechanical team, we have split into 5 sub-teams. So these start with our Aerodynamics and Sizing team, which is the first step in the design process of an aircraft like this. We're given different different mission requirements from the competition, as well as the other teams, the electrical and the software teams. From this, we can then create our general aircraft requirements so that we can then go ahead and design it, CAD it up, and then build it. From there, we also have our wings and our tail team. These kind of go together as they're both our aerodynamic surfaces. Moving on, we have our fuselage team, which houses all of our electronics, our batteries, and then it integrates with our wings and then our tail as well. And then finally, we have our UGV and antenna tracker team. So the UGV is a unmanned ground vehicle. Matt previously mentioned we're going to be dropping this from an altitude of approximately 150 feet towards a target, and then we will have to autonomously drive to another target on the ground. So we're currently in the very early stages of our manufacturing phase. So we've completed our design and now we're getting into prototyping our manufacturing methods. So I'll go ahead and walk you through our detailed design that we've put together so far. So from the sizing team, from our mission requirements, we've selected 25 minutes of cruise as our target, as well as a cruise speed of between 16 to 20 meters per second. This is going to allow our software and electrical teams to take images of the ground and not have any blur or anything like that. So we can get really good data from the sky. And then as well have a gimbaled camera so that we have very stable images for our software team. Our secondary objectives is large payload capacity of 1.5 kilograms for our UGV. The max weight for our UGV is approximately 1.8 kilograms given by the rules. We're shooting for 1.5 kilograms. And then modularity as well. We'd like to be able to transport this in a car so we can take it out to a local airfield for test flights. Moving into the actual system overview and the aircraft requirements, we used some previous example aircrafts to come up with a high wing design with leading edge taper. We're going to be using 2 electric motors and then this H tail shape with dual booms coming back. Within the fuselage, we'll have a couple different features: removable avionics and battery bays, bay doors, and then that camera and gimbal in the nose of the aircraft that I previously mentioned. So you can get a pretty good picture from the image on the right-hand side of the screen. This is our actual full assembly of our aircraft, highlighting each of these different features. Are there any questions so far or any comments before we get into the individual component design?
Sure. This is James Goppert. I just wanted to know some of your design choices here. Why did you guys choose leading edge taper for one? And why did the twin engine design instead of a big single pusher prop?
Those are 2 great questions. So to answer your first one with the leading edge taper, we knew we wanted to get the efficiency boost of the taper on either the front or the trailing edge. We selected the leading edge because that allows us to have our very square rectangular control surfaces on the back. So if we choose to do flaps in the future, we can have rectangular ones, but currently we're just looking at rectangular ailerons. We didn't have to mess with any geometry in the back, so it was just more simple. from a design perspective. And then the dual motors in the front, the 2 motors in the front, purely based off our thrust capacity. If we went with a larger motor in the back with a larger propeller, we'd be running into current draw limitations with our electrical team. So that was another kind of systems engineering decision that we had to make between the electrical and aeromechanical teams.
Okay, thank you.
Yep. Yeah. Any other questions before I move on?
I'd like to know, this is Charles Saff. I was wondering what your margin of safety was on your endurance time and distance numbers.
So off the top of my head, I cannot remember the distance numbers. Matt may be able to jump in here.
Yeah, really quickly, general distance number, I think we're flying about 10 miles total, and that's going to be, we want to have a built-in, I think, 25% safety margin for the flight time.
So both distance and time are 25%?
Primarily flight time is where we're building in that 25% margin. We're estimating about 10 miles as our total distance traveled. It kind of depends on the Waypoint algorithm that the software and electrical team come up with for the actual distance that we travel.
And what about a margin of safety or a factor of safety on the payload?
So this one, we're not implementing a significant margin of safety from the initial design, or we're kind of setting a hard cap on our UGV's team weight at 1.5 kilograms. Do you have anything to add, Matt?
No, I think it's good.
Yeah, so at this point, we're not implementing a margin of safety for the payload weight.
I guess we don't really have a dynamic payload. We know what our payload is going to be. So, it's pretty static. And we do have, there is a margin of safety. We can carry more weight than that 1.5 kilograms. So in that context, there is a margin of safety. I think we have probably another kilogram or 2 that we can carry on the aircraft while still flying at a reasonable speed.
Yeah, so I think to answer your question, our max gross weight will be approximately 1 to 2 kilograms more than what we're planning to fly with.
Okay, but out of, what is it, 14 kilograms total?
13 kilograms is our estimation.
13 kilograms total. So you can take a G delta of about 1/10 of a G. Just wondering if that's going to be enough for the maneuvers that you'll pull and that sort of thing. Something to think about.
Yeah, that's for sure.
Okay.
Awesome. Yeah, thank you very much.
Mm-hmm.
Okay. Well, I guess we'll move on into some of the detailed designs. So we'll start with our aerodynamics and sizing. This may help answer some of the questions that came up. Our preliminary approach, we went through a MATLAB sizing routine. So Nathan Broman, he was actually the team captain of the team last year. He generated a MATLAB algorithm for us to plug in our different mission requirements. And then the software would spit out our various different design requirements that we can then implement. So we use these solutions from our MATLAB script, plugged them into XFlyer, which is a theoretical simulation tool that's free. And this gives us a pretty good idea of all of our different aerodynamic aspects of our wings, our fuselage, and the tail for different stability analysis things. Finally, we used MotoCalc, which is another free tool for us to help size our motors and propellers. Since we did have to go with the 2 motors in the front, given the amperage draw, we use this tool a lot. Moving on, we're looking to do CFD simulations in the future. Hopefully we can get a good measure of our total drag on the aircraft so that we can actually get a better picture for our endurance. From the total drag, we can calculate what our cruise throttle percentage will be at, and then our current draw. So then we can calculate our endurance based on that and our battery sizes. So then moving on, this is the actual sizing results for our aircraft. So you can see on the left-hand side, we've got both our wing and tail, the different dimensions of that. And then our gross weight is approximately 13 kilograms with a cruise speed of 17 meters per second. So we fall right in that target range that we were shooting for of 16 to 18 meters per second for flight speed. So I can move on from this. Are there any questions with regards to the aerodynamics or sizing?
Why did you guys choose the twin boom configuration?
So that kind of originally came from a single motor in the back with a larger motor, larger propeller design. We were originally anticipating doing that configuration. It wasn't until after we kind of went through some of our sizing algorithms and then our X-Flyer setup that we realized we weren't going to have the electrical capability to do that. There would just be too much current draw, so we had to adapt the design and then go for the two motors in the front.
Okay. Have you thought about updating that to just like a single or vertical stabilizer and like a single boom, maybe save some weight?
That's definitely an option. We haven't considered that really yet. It's definitely something that we can look at doing in the future, and hopefully with the whole airplane being pretty modular, we should be able to just design certain parts differently so that we can accommodate that. We haven't taken a look into modifying the design at this point yet, though.
Another quick note, just going to hop in. Another advantage of having those two booms is that it makes it really easy for us to mount our motors on the front of the plane, because we just use the strength of those booms to mount the motors directly on there. Obviously, that's kind of a result of our decision. That's not what drove our decision, but we found that to be pretty useful.
Yeah, and I think it will help with the rigidity as far as the horizontal stabilizer as well. But yeah, just making sure that that's if there's any improvement you could do there, maybe looking at that again might be a good thing.
Okay, yeah, it sounds great. That's a good idea. Okay, so moving on, we'll talk about the wings. The primary configuration of the wing is currently no dihedral or any kind of angles, just the taper on the leading edge. So we're able to use one mid-wing that's flat. This mid-wing houses all of our interfacing components. So our fuselage mid-wing connector is contained within this, as well as our motor assembly and our dual boom tail assemblies are connected to this mid-wing. Because of this, we want really strong, robust design, something that's really bulletproof and we know we can have a lot of faith in. Because we're dedicating so much weight into the strength of this part, we decided to make our two outer wings that slot onto our mid-wing ultra lightweight. So we're using lots of different composite manufacturing methods to achieve this. I've actually got an example here that I'll show in a little bit, but the idea is to use a foam core rib that's spaced out and then carbon fiber skins on the upper and lower surfaces. So this will allow for a super lightweight design that is also really strong. We've got almost no torsion with our experimental prototype part that we made. And then we've got a little bit of bending, but we think we know how to solve that. It was just an error in the actual manufacturing process. Mr. Staff, it looks like, sorry, I'm just reading your question. So as far as the G limits goes, so for everybody, the question says, do you know what your G limits are for your structure? This will define your turn rate limits and gust load limits. So at this point, we have not decided on a G limit. Right now we're planning for 2 to 3 Gs. Is that kind of?
Yeah, so I think that to answer that question, it's going to be kind of an experimental thing. So right now, like Eric said, we're experimenting with these new composite techniques. And once we do manufacture those parts, we will be doing load testing on those to kind of figure out what our G limits are. But from preliminary testing, it's pretty clear that we can handle up to 4 or 5 Gs or possibly even more. So I think that that's definitely a concern or something that we should think about. But at this point, it's kind of we're pushing it off a little bit just because of our manufacturing. And if we do find that something doesn't match up with what we want, then we can refine our manufacturing from there. But I think that is something that we do need to keep in mind.
Real quick, did your sizing code, have you guys looked at like historic wing loading and power loading for vehicles in this competition? Are you in kind of a reasonable range?
Yep. Yeah. So the sizing algorithm, that was actually the very first thing that we did, was kind of compare it to a bunch of different papers as well as aircraft. Originally, we're looking at smaller lightweight aircrafts like Cessnas and Pipers, something very high lift, high drag, to kind of give us an idea, since we're ultimately trying to fly slow. So all of our calculations that came from that MATLAB script were actually within a couple percent of being like on the average of a bunch of different aircraft. So we're pretty confident in our sizing right now.
Okay.
Awesome. So 2 notes that I've got here. We're potentially looking at doing flaps between our tail booms and our ailerons. Currently, we're not planning on doing flaps just due to the complexity. And then we're also planning on implementing winglets and vortex generators. However, we've not started working on any of the aerodynamics with these 2 different bullet points. So this is something we're looking at doing in the future, and would like some input on those maybe at the end of the presentation, just because I know we're going to be running short on time. Anyway, so we'll move on. So, oops. Okay, so this is a good look at our mid-wing design. You can see our 2 center ribs. They have tabs that extend vertically downwards. These interface with the fuselage. You can see on the bottom right side of your screen, this is how our vertical tabs extend down into the actual skin of the fuselage. Then we'll run a couple bolts and nuts horizontally through the actual fuselage and that rib. So ultimately, the load from the mass of the fuselage will be directly transferred through the ribs and then into our spars. So the spars and rib structure of the mid-wing is where we're generating our strength. You can also see our booms. These are actually sleeves that are mounted to the ribs and the spars. This allows us to take our tail booms, slot them into those sleeves, and then we can bolt them in place. It's very modular, and we know that if we choose an inside diameter and outside diameter that match, we should have a perfect, strong connection there. Moving on, we have a large spar and a relatively small alignment spar that extend out from the mid-wing. This is what our interface will look like for the outer wings. So we can simply just slide our outer wings directly onto these spars. And then our current plan is to use a bolt internally within the wing to connect the 2 together and hold it so that there's no, let me see if I can show, so that the actual interface between the outer wing and the mid wing don't go like this. We've had issues with that in the past with our old aircraft. We have the boom that extends across, but it's still, there's a little bit of give within the actual material, and that boom bends a little bit. So we're trying to avoid that by adding those bolts and nuts in there to keep everything super tight and snug.
I don't know if I'm just looking at the diagram wrong, but it looks like you're drilling a hole through the tail boom to put the spars through.
That's correct. So that's the sleeve that I mentioned. So in the image here, that's a sleeve that's slightly larger than the diameter of our tail boom. The tail boom then slots in the last half of it. The last half is approximately 1 foot long, so that gives us a good surface area and good lever arm for that tail boom, so that we know that we can transfer our load without any bending or wiggle or slop or play or anything like that.
I think, if you try to drill through carbon fiber, it's going to weaken it quite a bit. If you can avoid actually having to drill through it, if there's some kind of just a joint that you can make, maybe out of wood or some other material, I think it'd be a lot better than actually drilling through the carbon fiber.
Okay, yeah, that's good feedback. We've done that before, and we've cracked a couple tubes. So we'll definitely look at that. We're playing around with some sizing, but that may be a better strategy, just to avoid drilling through the carbon altogether. Awesome.
You might try just wrapping it with an aluminum to drill through and carry that load.
Okay, that's not a bad idea either.
Yeah, I think carbon fiber on carbon fiber is a bad thing structurally.
Yeah.
Okay, awesome. Well, we'll definitely take a deeper look into that. anyways, moving on to the outer wings. I apologize for rushing. We're just a little bit pressed on time. Moving on to the outer wings. This is our ultra lightweight design. So you can see every 20 centimeters, we have a foam core carbon wrapped rib that is then epoxied into two skins. We have an upper skin and a lower skin. Yeah, I can show the example. So this is what one of our ribs looks like. You can see we've created a negative mold out of MDF, and then we were able to put this in here and use a foam core to press it out on the outside. I've gotten a picture of it a little bit later in the slides, but we created a test piece, and we're approximating our full wing, our full outer wing, which will be about half a square meter of area. We're approximating it to only be about 1.2 kilograms of weight. So we've got a really large wing with super low weight, and based on our prototype experiment, it should meet our strength requirement as well. We need to actually build it and go through load testing before we can confirm it. But based on our prototyping, we are confident in this design.
What about torque in the outer wing?
Yeah, so actually I can show the part, excuse me, sorry. So this was our test part. It's actually our horizontal stabilizer, but it uses the exact same construction method. So yeah. I'm standing here, I'm not Superman or anything, but I'm standing here. We've got a couple errors that we made in the actual manufacturing process, and we've made notes of that so we can correct them. So on an unperfect part, it's pretty strong. We haven't measured it, but I don't anticipate we'll be having torque that much when we're actually in flight. But yeah.
So do you actually run fibers plus minus 45 out there, or are they all longitudinal?
So we've got 2 layers of 2x2 twill, and then those are on the outside of a unidirectional ply. So we're running everything at 0 degrees currently. We're thinking about doing some experiments with laying them up at 45 degrees. We'd like to stay to 3 layers maximum in our skins.
Yeah, and another note is we're trying to keep that layup symmetric as well, to kind of avoid, bending and different types of couplings structurally. So right now we just have, twill, which is 0.90. Then we have a 0 along along the length of the wing that's unidirectional to get that bending stiffness. And then we have another layer of twill to keep that symmetric. So we're definitely open to experimenting with having a plus or minus 45 layer in there, but we do want weight is a concern as well. So that's
sure. I'm just thinking you probably have more than enough bending stiffness. So I'm worried about torsional stiffness with no spar out there. That's the only thing that's driving my question.
Okay.
Okay.
Okay. Yeah, we'll definitely keep that in mind, and we'll definitely do some experiments, even if it doesn't make it into the final aircraft. We'd like to know.
Yeah.
But go ahead, Matt. Moving on to our tail, I'll kind of speed through this very quickly since it's almost identical to the outer wings. The actual internal structure of our tail surfaces are going to follow the same construction method as the outer wing. So I showed here, this is our actual horizontal stabilizer that we've got. And then the outside, let's see if I can show it. There's about a 1-inch slot on the outside here that then slots onto a 3D printed part. That you can see in the bottom corner. Let me move. I don't know if you can see that or not, but in the bottom left corner, that shows a 3D printed part that wraps around our 2 extending tail booms. We're gonna secure it via epoxy. So we should have a really rigid, strong connection between our tail booms and then our actual control surfaces. Okay, moving on. Oh, thank you, Matt. So I'm going to pass the presentation off to Andrew for the fuselage. Andrew's been heading it up. He's our systems and integration lead. So he'll go ahead and introduce himself.
Hey, I'm Andrew. I'm a junior in UMNI, and I've been working on the fuselage and doing systems integration. So the main point of the concept of the fuselage is that we're going to have some a load-bearing skin, since we're going to be using carbon this year, and we're going to have some carbon foam core ribs like I have here to support the load. One big design concept was centering everything around the UGV, which is that ground vehicle you can see. We're trying to place it right at the CG, so when it drops, it doesn't affect our airplane's flight. We want easy access to all of the electronics and battery systems, so that was important. We need some kind of bay door or release mechanism so we can get that UGV out of the fuselage. And then, of course, the camera gimbal is why we're flying, so we need to have that correctly. Right now, we just have a fixed landing gear. It's not steerable and it's not retractable. Those are maybe stretch goals that we can get to later, but for now, we're not worried about it. More into the structure. So these are carbon fiber foam core ribs. This is about 3 layers on each side. Foam core, it's relatively strong. I think it could be improved, but I think that we'll have enough strength from there in the end, and we'll be able to mount the landing gears that you can see directly to the ribs as a strong connection point. And then we need a strong interface from the wings to the fuselage. That's really important to us because if something's going to fail, it's probably going to be there. So you can see these very long carbon fiber sheets that are attached to the ribs, and we're just planning to have a very strong member there that will be screwed in at multiple attachment points along all 4 of those ribs, and then the wing rib will screw into that other long plate. So yeah, 3 to 4 layer carbon skin as support. That way we can get a lot more out of a lot less weight, and we can also add more of these supports later, and that's important for us. Any questions so far?
Are you going to have the skin off when you do the wing attachment and then put the fuselage skin on after that?
No, so yeah, the top of it underneath the wing will be completely open.
Right.
That way we can just slide the whole thing down, and we can have access into things like the dropper and UGV and the batteries.
How do you get access to the mating holes to attach it?
So we think we can we'll go up through the bay door on the bottom. It's probably a good like 6 by 8 inch hole that we can just reach up through and screw through. And worst case, if that does not work, we'll just go directly through the skin on the outside because it's only going to be, you know, 1 millimeter or 2 thick. So that wing rib is right pressing up against the skin. We have a couple options.
Okay. Probably the second idea is better than the first one.
Okay, noted. Any other questions? Okay, so then moving on to the bay doors. This is our concept for now for the bay doors. It's going to be dual bay doors that open just as you know normal bay doors look like they would, and we're just going to have a servo with an arm that will be moving this linkage, the slot on the carbon there. We are worried a little bit about that being kind of a control surface, but we do think that if this is a problem, we can get rid of it and go with something a lot more low tech, like just a sheet or something that can tear off. We're not sure, but we think we have other options. For the UGV dropper, that's on the right there. You can see it's just a servo and it's just got a linkage that will twist and drop UGV. That seems pretty simple, so we don't anticipate any problems with that either. And then lastly, the camera gimbal. So we just have a gimbal in the dome at the front. That's our camera. We'll just mount it to the gimbal that has 2 degrees of freedom so we can get really stable pictures, and we can rotate it manually for one of the software tasks that we have to do. We're planning to leave the bottom of it open right now for airflow, but we can always close that off with acrylic. That's it for the fuselage. So are there any questions?
I think my one concern is how are you transferring the longitudinal loads in the fuselage, like especially the landing gear attachment point? Looks like it's attached to that one rib and it might just kind of rip off. You know, you're relying on the skin to carry all that load?
Yeah, we're hoping the skin carries a lot of it. We're also going to make sure that that rib itself is much larger than the others likely.
Mm-hmm.
Also hoping that that large but kind of plate will also transfer the load. So we're hoping that a combination of all of those will be enough.
Okay.
You're really carrying the longitudinal loads through those wing attach fittings, right?
Sorry.
I am assuming that those long plates that go all along the sides of the fuselage and attach the wing or part of the wing attachment also go all the way back to that aft rib
Yeah.
and to the forward rib. I mean, that's pretty good continuity from fore to aft.
Yeah, they'll go all the way from the back one up all four of
all
them.
the way to the front.
And if we find that that's not enough, we'll actually continue it all the way to the front. And we also have this plate that's carrying the batteries and that stuff there in the middle. So the plate underneath will also be carbon, and that will provide a different support between those ribs in the front.
Yeah. Have you considered a screen door type roller system to just roll the bay door open and then that closed?
We haven't. That's a good idea.
That gets rid of the extra control surface issue and maybe gets rid of a lot of the actuation issues.
Right. Okay. We'll look into that.
Yeah, you can make it a spring loaded affair and it just closes when you're done.
Right. Okay. UGV?
Yep.
Okay, now we're going to talk about the UGV, so I'm going to hand it off to Evan.
Okay. Hi, my name is Evan Cam. I'm a junior in mechanical engineering. I've been working on the UGV. So our design for the UGV, as you can see, is a two-wheeled vehicle with a skid on the back. So because it's two-wheeled vehicle, we have to have two independent servo motors so that the wheels can go at different speeds so that we can turn and things. So we have a rear skid, like I said. We tried to keep the center of gravity as low as possible just to keep the UGV stable. We have a weight maximum of 64 ounces, but we're trying to keep below 1.5 kilograms, I believe. We have internally mounted electronics, like you can see right in the middle there, that little black spot. That's one of our servos, and it's mounted to the wall so that it's like very stable. And then there's two other walls side by side just to make sure that those motors don't move around. Parachute recovery system. This is something that we haven't had a lot of progress on. We started just trying to get our UGV intact, and then we can worry about the parachute. But our thought right now is to have servos on either side of the UGV on the outside, and then have the parachute attached, and we can like try and reel in the parachute so that it's not getting all tangled up in our like wheels. And then lastly, suspension has asterisks because that's also something that we want to consider moving forward, but didn't consider a whole lot in our initial design. But one thing that we thought about is either adding suspension to like the wheels itself or to the skid in the back, adding some sort of suspension so the skid can take a little bit of an impact. So, if you guys have questions or input, I would love to hear it. Yeah, in the next slide, so here, there's some more pictures for you guys to look at too. Oh, here, I'll do some explaining before questions. So, in the picture in the middle, you can see that there's like a sprocket attached to the motor and then another sprocket attached to the axle. And then we're just going to use a chain so that the motor is not directly attached to the wheel so that when it takes any sort of impact, it doesn't affect the motor as much since it's not directly connected to it.
So then will it be chain driven?
Chain driven, yeah.
Okay.
What else?
What kind of tires are you guys going to put on it? I imagine if this is like in grass, you're going to need some pretty good traction, right?
Yeah, so we have some 3D printed like TPU tires. It can kind of take a little bit of an impact, so provide some cushion, and then we add like a little bit of traction, like I don't know how to describe it, like just like lines on the like rigid lines on the bottom to give it some grip.
Yeah, just building off what Evan said, or what Evan said. Last year we had, I think, 8-inch diameter wheels that we manufactured out of. It's a kind of thermoplastic that you could breathe. It's almost like a rubber, and so
Okay.
if you print it with thin walls, then you can actually get a pretty good deflection. I think we had about 1/2 inch deflection last year. Dropping it from a relative speed to what we might experience during the competition. So that was able to kind of absorb the shock from hitting the ground. So I think that's going to be our primary method of mitigating that risk. And then also it provides a good surface to drive with. So
Where's the CG of this rover at?
Sorry, can you say that again?
Where's the CG? The center of gravity on the center of mass?
It's more towards like, see where that middle wall is? It's like right in front of the water bottle by that middle wall. Is more where its center of gravity is. So it's a little bit,
I just think you might want to keep track of it just to make sure you get enough traction on the tires.
yeah.
And then another comment, it's also relatively low to the ground, which is going to prevent any sort of, flipping or rotation.
Okay.
Thank you. Good job, buddy. Okay, awesome. So we've only got a minute or two left before we move on to the software team. We want to stay pretty close to schedule. So I'll just kind of breeze through the last couple slides. Part of the aeromechanical team, we're going to be designing an antenna tracker. One of the challenges with our software and electrical teams is the need for a very high bandwidth data link between the aircraft and the ground station for our image transmission so that we can actually get our data from the aircraft down. We're choosing to use an omnidirectional antenna on the aircraft and then followed up with a unidirectional antenna on the ground that we can then point through a pan and tilt 2-axis antenna tracker. Our current plan is to use existing commercial off-the-shelf products such as Pixhawk as our flight controller, or in this case, ground station controller, and then existing firmware that links up with our ground station software. So from a controls point of view, hopefully we have it covered. This is something we've never attempted before, so it's definitely going to be a work in progress. We're planning to start this project up in January when we come back from winter break. And then finally, moving into just kind of our manufacturing methods. We already showed off some of our parts. We'll be using additive, subtractive, and different composite manufacturing techniques. All of our composites that we've done so far are just using traditional wet layup. So laying our fabric in our molds and then painting our resin in. In January, we're actually going to be starting to use resin fusion. So we've been doing quite a bit of research, and then we were able to secure some grant money. We're going to be hosting a little composites workshop where we teach people how to do resin fusion, and then we'll also be using that for our existing parts on the aircraft. So we'll probably go from like an A finish to like A+ is kind of what we're anticipating. So the images on the screen were the parts that we showed today. And then these are some examples of our molds. We do all of our mold prep in-house and everything. All of the machining is done at the machine shop here. So this is definitely something for a future meeting to potentially explore a little bit more since we're out of time today. But we just wanted to thank you guys very much for taking your time for the aeromechanical team. If there's any final comments or questions, we probably have like about a minute to go through them quickly. If not, I'm sure that Matt has a way that we can communicate after the meeting to answer questions. Okay, awesome. Well, thank you very much. I'm going to pass it over to the software team. I think there's going to be some people coming in and out of the Zoom meeting. So yeah, thank you very much, everybody. And I look forward to talking with you guys again, hopefully soon, and continuing to receive your feedback. So thank you.
All right, we're just going to transition really quickly over to this other Presentation. All right, for those of you who weren't here before, my name is Matthew Updike. I am the president of Purdue Aerial Robotics. So this is going to be the software presentation where we focus on computer vision and machine learning techniques. A quick background for those of you who weren't here before on the organization. We are Purdue's largest student aircraft build team, and we're working on building an unmanned aircraft from A to Z every single year. So we have three main components of our team: the aeromechanical team that builds the aircraft. We have the electrical team who does data link and communication tasks, and then we have the software team that's focusing on a pretty complex computer vision component to our competition. So the way that the competition works is we start off by taking off autonomously. We then navigate a bunch of waypoints that you can see here on the outside while kind of avoiding these obstacles that are highlighted in yellow, infinitely high cylinders. And then the main software tasks comes towards the end. And if you can see this blue shaded area here, essentially they'll be giving us, they'll be placing on the ground a bunch of targets that are about a foot or two in diameter. And we have to relay certain characteristics about these targets in real time. So we have to give things such as the alphanumeric on them, the color, and we'll run through this in a minute here when I pass it off to Diego. But hopefully this gives a bit of a background in the competition. And here's just a little schematic. So, obviously takeoff, doing the waypoint navigation. There's a kind of rover drop section to the competition, and then the software portion will happen at the end. So I'll pass it off to Diego here to talk more about the technicalities of the computer vision.
Hello. I'm Diego Montes. I'm the software lead for Purdue Aerial Robotics, and I'll be kind of walking through our software design. We're using a lot of deep learning techniques and computer vision, along with some other interesting stuff like GANs to do our, the work. But more or less what the challenge is we have these shapes that are about a foot long, and they can be bigger, and we're observing them from 200 feet above. And these shapes can be, different shapes, obviously, different colors, and then they have a letter on them or an alphanumeric, anywhere from 0 to 9 or A through Z. And these can be any color as well. So we have to be able to tell all these characteristics from that high up using our computer vision models. And we also have to be able to say some other things like GPS location, the rotation, and we also have to detect one object, which could be a firefighter or a person of interest. But going over kind of the system design of our actual models and how we process the image. For the intake, we take an 4K image from our image sensor or camera. And we have a detection model that actually tells us where the targets are, but this model only takes in 640 by 640 images. So for a 4K image, you can imagine that split up 28 times, this gives us what we're looking for, but that's 28 times the detection model will have to process it. So is there any way to mitigate this kind of, lack in the throughput? And so that's creating kind of like a slice classification model. And so this doesn't tell us where the target is. It just tells us, does this small chunk of the image actually have a target in it? If it does, okay, let's continue on with the process. If it doesn't, let's throw it out. So that's its main goal. And it's meant to be as lightweight as possible, reducing the throughput a little bit, but not as much as processing all 20 per image. After we got an image which has, an almost guarantee of having a target, we put it through our actual detection model. This will tell us where are the targets, what type of shape it is, as well as the confidence it has in its prediction. We crop at each model, and then we do the characteristics. We say, what's the alphanumeric we're seeing? Is it an X, for example, in this picture? And what's the color of the base shape and also the alphanumeric? And so all these models are developed individually, and then we put them all together and try to, increase performance through all of them to increase the overall system performance.
Really quickly, for those of you who just joined for the software presentation, please feel free to interject or to critique during the presentation. You want this to be conversational. So if there's anything of a note, then please feel free to kind of join in.
For sure. And so one of the biggest problems here is if we're training machine learning models that feed off data, how do we get this data? If you can imagine, you'd have to cut these out from kind of cardboard and spray paint them, wait a little while. So optimistically, if it takes 10 minutes to make a cardboard target and there's 30,000 different combinations of target, for a machine learning model to see the full picture, we'd have to spend about 208 days, 24/7 making targets. So that's just not feasible. So what we have to do is synthetically generate these targets. So for example, on the right, you can see we kind of synthetically generated some of the targets in that image. And it takes about 5 milliseconds to make a target. So it ends up being, 2.5 minutes of making 30,000 targets versus the time it would take us to do it manually. And so on the top there, you can see kind of our synthetic version, and on the bottom is the actual version. So our synthetic isn't bad. As you can see, if I took away the labels, you might get fooled. But there's still some things missing. A lot of the things we do in the data generation are, can we modify the properties of the shape, like the internal angles, the size of it, just how the shape is actually structured. Then can we adjust the color? So different shades of blue and green. And then can we like shift the way we're looking at the shape so that we're getting like these weird transforms and really increasing the variability that the model sees. So is there any way that we can bridge this gap between, pretty good and excellent, undistinguishable from real? And so that's kind of an image to image translation process. So cyclogams are models that allow you to change from one image to another image. So for example, if we have a handful, maybe not that many because it's labor intensive, of real targets, and then we have all these synthetic targets, can we map some way between them, and that way we get real targets from our synthetic targets? And so we use the research paper over cyclogams to do this, but the research paper was originally meant for 256 by 256 images for translating horses to zebras. But our images are 36 pixels by 36 pixels, so it's much less. So it ends up creating these checkerboard patterns. If you look at in the top right, you see that kind of third image. It created this checkerboard, and it's now it's super clear that it's not real at all. And so we had to modify the original research paper model, and so now we're doing that. And it's removing these checkerboard patterns, but there's still some work to do. But these are kind of an effort to improve the realisticity of the synthetic data that we actually generate. So going on to the actual models themselves, our slice classification model is just a binary task. And so it's a very shallow neural network. It just has 3 convolution to max pooling layers, and then a final layer to tell us, is this a target present or is there not a target present? And so this was trained on 1,000 images where there was a target in the background, and 1,000 images where there were no targets. And so this came out to be 85% accuracy, which isn't bad because it's telling us that, if we're already filtering out a lot of those just empty backgrounds, we're already doing good. And you can measure the throughput of a model using the number of floating point operations it takes. And this one had 835 million, which isn't bad. And I'll talk about it more later. But we have a budget of 21 trillion floating point operations. So if we ran this model alone, it could run pretty fast. So this is exactly what we're going for. In terms of the actual main target detection model, where it tells us, where is the target and what shape is it? There's about 13 distinct shapes. So you can tell some of the harder ones would be a circle, octagon, heptagon, hexagon, and where do the lines blur between that? And so we use the popular YOLO neural network architecture. And so, since there's so many variability of like different architectures that people have gotten written their own research papers about, we're able to adapt this for our task. And so we trained this on 30,000 entirely synthetic images, and the video to the right is on real images. So it's performing pretty good for only having seen synthetic images. And this is 4.5 billion flops. So that's still pretty good considering the 21 trillion. So we're getting high performance at low cost, and this got an 83.2 mean average precision, which is, if you're not familiar with mean average precision, you can kind of compare it to accuracy. Some of the challenges we face here, the model struggles to predict confidently. If you remember earlier, I said that the model tells us not only the shape and where it is, but also its confidence in it. So it'll say maybe this is an octagon 60% confidently, but it won't be able to tell us that at maybe 90% confidence. And we're having trouble, breaking that threshold and being able to predict all these targets, above 80% confidence. Another problem we have is that because these are just synthetic images and we haven't bridged that gap yet, when we're training, it stops learning or improving on the real images after some time because it's adapted so much to the small variability that exists in the synthetic images. And also we have these, the images can be longer than 1 foot. and that's all we've tested on. So, that might be a good thing because we're saying on the smallest level, are we able to detect this? And, if we expand it, we might do better, but we haven't tested this. And, and the image to the left just tells us if we adjust this confidence threshold. So for example, if we detect something with 10% confidence, we won't count that, right? We won't send that to the judges or make predictions on that because we're not confident at all. And so this tells us, where should we put our thresholds to get the max performance? So right now it's telling us that, at 41% confidence threshold will give us the max performance. In terms of alphanumeric classification, after we've actually detected the target and cropped it out, how do we tell the alphanumeric? There's 36 distinct classes here, and you can imagine that this is pretty hard when you think of 9 and 6s, but now think 3s and M's and W's and E's. So it starts getting pretty difficult when these can be anyway, and the quality isn't always guaranteed. So we trained this on 122,000 different images, and these had a lot of augmentation done to them, random rotations, perspective, blur. And this, again, just like the slice classification, is only 826 million flops. So for getting 93% accuracy at that speed is pretty good. And so, some of the ways we did this is we used this popular base model called exception, and we used pre-trained weights and transfer learning. And so what that does is in a neural network, some of the initial layers detect edges and straight lines. And so we use those base features, and we're able to later just add some final layers that take those base features and then turn those into, okay, is it a 9? Is it a 6? Is it a 3? And so on. And so to do this, we also use the learning rate scheduler, which basically just tells the model to, tune more slowly near the end. And originally we did this with only, images that we synthetically generated at 96 by 96. But later we switched to generating images that ranged from 16 by 16 pixels to 256 by 256 pixels. And we just resized all of those to 96 by 96. And this actually significantly improved our model performance since it's able to see a wide range of targets, even if they are rescaled later on. In terms of color classification, this is a little trickier because if we wanted to detect both the alphanumeric and the base shape color with one machine learning model, it would require quite a few custom components since it's not a usual task that's done. So we use kind of an algorithm as opposed to a machine learning approach. So what we do here is we crop the image, and since our detection target might pick up on some of the runway or some of the grass surrounding it, we do kind of a symmetrical crop around the image. After that, we say, okay, what's the most common pixel in the image? We get that, we say, it must be the base shape color because we're assuming that the alphanumeric isn't going to be the largest thing in the image. And then we remove that all from the image and see what the remaining color is, and we assume that's the alphanumeric. And so we've had some success with the alphanumeric, but more success on the base shape where we're getting about 92% accuracy. So there's still a lot of work to be done here, and we're planning on trying a machine learning approach as well, just to see if there's any merit in that. In terms of edge computing, like I said, all of these models on a server, there's no problem. We don't have to worry about performance, but on the edge, like in the air, we have to worry about, how are we going to run this? What speeds can we reach? And so we're using the Xavier NX, which is a NVIDIA product. And this gets about 21 teraflops at int 8 precision and 1.4 teraflops at float 32. So even at 1.4 teraflops, we're already getting 200 frames per second, not counting pre-processing and post-processing, which is already pretty good. So it gives us some room in our models to make them even bigger and more accurate. And this comes with power consumption. So if we're still getting 200 frames per second when we're at the the accuracy we want to get, we can lower how much power we're consuming and do that. And some of the things we haven't worked on, but we're planning on working on, there's a lot of open source tools out there that specialize in optimizing neural networks, such as TensorRT and ONNX. And by using these tools, we can actually slim down our neural networks to be even faster than you saw before, from the 800 million floating point operations to maybe even 600 to 500, while still maintaining the same accuracy. So by doing this, we're able to deploy these this complex system all the way to the edge. And so that's all about software and what we're working on. Does anyone have any comments or anything like that?
So I have a comment. I don't know if it's appropriate to interject it now. Looking at your sample images, from the altitude that this drone is flying at, almost all of the objects are very, very small in the field of view.
Right.
And when you, once you crop them, they are extremely low resolution. And that probably more than anything else is impacting your accuracy, your mean average precision, and all of the components in your pipeline. If you have the option of putting in a optical zoom lens on your camera, and even more so if you have the option of putting in a pan tilt unit that doesn't actually pan the entire camera, but just has a mirror that is panned and tilted, that you can get high speed pan tilt. If you had just the high level pass of YOLO to spot the objects, and then you quickly panned and zoomed into each one individually, and then ran just some other classifier, even a fairly low resolution classifier like 64 by 64, 128 by 128 pixels, you probably get much higher accuracy on the back end of your pipeline at very, very low computational cost.
Right. I think that's always been or up to now has been our bottleneck, the resolution that we can get it at. But that's a good point that we're planning to add those kind of more meta algorithms on top of our models to see if after detecting with YOLO, or we can go back and improve resolution, and that way we can improve the alphanumeric and color models that we'll work on, or if we can just from the start improve the hardware that we're using to improve that resolution. But just to note, the images right here on the screen, that'd be like the lower bounds of what the images are. Generally in the competitions in the past few years, they've been shrinking the size of the shapes every single year, but they've been generally pretty big. So we're testing the lower bound actually right now. But you still make a fair point about the kind of bottleneck that the resolution gives us.
If you couldn't afford to do kind of a pan tilt, another pan tilt camera or something like that, or actually being able to adjust it on the fly, you could have like a fixed field of view for that high resolution camera that your path planning actually sees with the low res or with the wide angle all of the targets, and then kind of plans a path so that the field of view of the high resolution passes over it. Would be kind of a cool approach.
Yeah.
Another thought I had would be all of these targets are lying on the ground facing straight up, right? And the ground is fairly flat. So all of these like optical distortions that are effectively skew from the camera matrix, you can remove before you send it to the machine learning algorithm. So it doesn't have to see R at like a 45-degree angle from the side. You can remove that distortion and give it R as if it were just like flat on a page, which might make it more robust. And then, so those are some ideas I had.
Right. I think our initial thought process with the distortions were with the perspective was that if we do that, the model will generalize better since the synthetic won't be, match the realisticity of the actual data. We're not exactly sure. We haven't trained without all these distortions. So we're not sure how that would impact model performance, but we'll definitely try it out.
I have
I was saying, oh, go ahead. Yeah.
Sorry, go ahead. You can finish up.
Yeah, I was just going to say, I think it would be very easy to, if you know where the aircraft is, where you see it in the camera, you should be able to remove the distortion out of the real image is what I'm saying. Right.
Yeah, I think right now we're flying pretty high, so hopefully that's not a problem.
Okay.
But I think on the hardware level and just a little bit above that, we can do some transformations to remove those distortions.
Okay. Yeah.
So I have a question more about the plumbing of how you're going to get data to and from the system to the base station, wherever the processing is happening. From the perspective of as a data engineer, my perspective is like less on the actual the deep learning algorithms and more on how are you going to do this in a low latency fashion? What are you using to get the data to the system that's doing this processing, and how are you going to get the processed output back to command the craft?
Right.
Or even more basic, are you doing this all on board with the Jetson, or are you transferring the data to do off-board processing? That wasn't even clear in the first place.
Right. Like I mentioned with the device we're using right now, optimistically, it's seeming like we're going to be able to conduct inference at far greater than the speed we actually need. So if that's the case, then there's no reason to have to transmit large 640 by 640 images to the ground. However, if it turns out that we need to expand some of our models significantly in order to do that, or we're not counting in some of the post-processing, like a non-max suppression for the YOLO model, or the impact that has, then we will have to transmit some of the image down. And actually, electrical is going to talk more about the data transfer for that.
Okay, so this is on the craft then. So the camera and the processing are next to each other.
That's right. Yeah.
Okay, that makes so much more sense then.
So I was wondering if you have an existing aircraft, an existing UAV that could take this system and get some flight experience with it before you have to implement it on your actual physical model.
Yeah.
So you could do more testing before you actually have to integrate the two.
Yeah, that's exactly right. I think the only reason we've hesitated from that is because we only have one of these edge devices, and it costs, I think, $800. And if we crash it, it breaks pretty easily. But that's definitely our goal after we make sure that we're all safe to go, and we probably have a spare one where we're going to definitely try it out, and that way we don't have to wait on the aircraft's completion.
So then my other question is, do you require dynamic isolation from the vehicle or some kind of damped attachment in order to keep vehicle vibration from distorting your images?
Yeah, I think that's actually something that's really important, and that's why we have that gimbal that's built into the aeromechanical side of things. We're hoping that there's going to be some kind of dampening system on there. That's the plan right now. There should be a dampening system on the camera itself and also on the attachment from the gimbal to the aircraft. So we're hoping to have close to zero vibration, but that could lead to some major problems if there were to be vibrations. And then going back to your question from before, so right now, we're not putting this whole edge computing system onto our previous aircraft, but what we are doing is flying both our previous aircraft and different drones that we have access to get video feed at what would be somewhat realistic conditions to what we would experience with our aircraft next year. So that's kind of how we're combating, building the aircraft and doing testing at the same time.
Okay, so you are doing some real live testing.
Yeah, that's right.
At least for video images. Okay.
This video was kind of this video among some other videos we kind of have as our test set. So, our performance here is kind of how we measure how well we're doing with the synthetic data and also our models. And it's not doing too bad. I mean, some of the confidence can be boosted and it's not detecting some objects. And that's kind of how we say, oh, rectangles aren't working in our synthetic. Are we stretching rectangles more, or what can we do? And so we kind of have a loop there in our development.
Okay.
So I had just a few thoughts. One question was, why not train these models jointly? Because these errors, if you train them separately, the errors will propagate. So like if you don't capture it in the beginning, it's kind of like a failed case automatically for the future parts. So like, if you're detection is 85% in the beginning, it's never going to be better than that with the full pipeline, right? So that was one basic question of why not train these jointly.
That's a really good idea. I don't think we've actually thought of that just yet. I think it's because we've been kind of developing these models separately, or the architecture of them at least. So we haven't had that opportunity yet. But I think the orchestration of them into kind of one training session will actually be better. And that way we can measure performance accurately versus separately, and then kind of be disillusioned on what our actual performance is.
Yeah. Okay, great. And the other thing with cycle GAN, two thoughts on that is you could make a cycle GAN, the generator, to be much simpler. You don't need it to be as complicated as it currently is. For example, you could have one simple convolution possibly, because all you really need here, from what I can tell, is kind of some blurring, some color distortion, maybe a little bit of rotation, but you don't need like a complete transformation into a new image. And that's using a simpler kind of generator is more likely to transfer well as far as in new situations. So you might want to think about using a much simpler generator.
Up to now, when we've been doing this, the discriminator loss has actually been reaching 0 pretty quickly, signaling that it's reaching a failure mode. And that might just be because the generator is so overly complex that it's generating 4 images, and the discriminator is able to tell them apart almost instantly. And the checkerboard, these images were actually trained 25% of the way because we haven't had a lot of opportunity to work on this. The way we remove the checkerboard pattern is to remove some of the deconvolution layers and the generator, and replace those with the resizing layers and then convolution layers, because some of the convolution layers like overlap and create those checkerboard patterns. But we can definitely try stripping more layers out and see if that has any effect. And
one other point on that cycle GAN is you don't actually need cycle GAN here. You only need one direction. So you don't need to go from kind of realistic images back to your synthetic images, and that's what cycle GAN is kind of meant to do, is kind of go from one direction and then back. But in this case, you only need the forward direction. You only need to go from synthetic to these kind of realistic or modified ones. So you could simplify the training also to actually only have one GAN adversarial objective going from synthetic to this kind of realistic thing.
That works. I think we can pull out the B to A kind of generator pretty easily, so that'll help. Good talks. Thank you.
Hey, Diego.
So along those lines,
Go ahead.
It would seem to me that YOLO as a detector and localizer is also serious overkill, because your problem here has some very particular characteristics that are in this particular competition that aren't shared with what YOLO was really designed for. Like, first of all of your objects are all approximately the same size, and your altitude is fixed, and you control your altitude. So, and all of the views are all frontal parallel. So they're all the same size. So you don't have to have, anchor boxes or default boxes of different aspect ratios and different scales and all that kind of stuff. And in fact, all your objects, you don't even need synthetic data generation. All your objects are synthetic. You only have a particular set of whatever 13 distinct shapes, and they're all geometric shapes. So I don't know how much variation there is when they make these physical objects cut out of cardboard, but you could probably make, very old-fashioned style computer vision, like Huff transforms, to detect circles and octagons and heptagons and hexagons and the like. and just use the features that you get from those Huff transforms as input to, you know, a much simpler classifier. The classifier itself could be a neural network, but the feature extractors don't necessarily have to, because you're not using the power of a full convolutional system, which is got all kinds of texture associated with it, and all kinds of arbitrary shapes associated with it, and all kinds of arbitrary projections associated with it, and the like. So if you thought through a completely new architecture, you probably could, as David suggested, train it end to end with all of the aspects that you're going to extract, the shape and the color and the OCR, but particular to the characteristics of this problem, and you probably can tune it to have much higher accuracy at higher speed.
The YOLO network we're using was based off YOLO v3, the one by Alexi, but this is actually, that neural network has, I want to say it's much bigger. This is actually a custom neural network that we did, that we stripped down. We took out a lot of the convolution layers.
Okay.
That's how it's only 4.5 billion flops, where the original one was, I want to say it was in the hundreds of billions of flops. So it was much bigger. Even YOLO v3 Tiny was bigger than this one. And we thought, because the kind of the feature extractor thing that we should definitely try out. We've been trying some of that to do it kind of algorithmically without the machine learning. We haven't had much success with that, and because it's so easy to train these neural networks and strip it down and still have that accuracy from the original architecture, we've had some success. But we'll try the feature extraction and then trying the classifier, because that's something we hadn't thought of before.
Yeah, and I'm sort of surprised that the one part that you did algorithmically, which is the color classification, would seem to me to be the part that would most benefit from machine learning approach and training approach, just because that's much more dependent upon variation in lighting, and it's probably a much noisier thing to try to build a hand-coded classifier for. I would expect that, given that these are all synthetic objects that are all painted, that if you got enough training data and just threw it into a fully connected layer, you'd get much higher accuracy on color classification on the output.
I think originally we thought, when we got to the color classification task, we thought, it's just pixel colors and that, and it should be easy to do algorithmically. But now we're seeing that it would probably be easier to do a machine learning approach. We actually working on that just now to to pull out those pixel values and just say with probably 2 fully connected layers to do that. So we're gonna probably try that out in the next week or two. Thank you. I don't think we have much more time for questions.
Yeah, if we could just do like maybe 1 or 2 more questions and wrap up here, so we can move on to the electrical team. If anybody has any last minute questions, feel free to share.
Just really quick, can you guys hear me? Yeah. Okay, cool. So do you know what the drone, the initial drone field of view is that you took these sample images?
Julie, do you know the field of view of your camera? The field of view for your drone camera, do you know what it was?
I don't exactly know the width. I mean, the resolution is 4K 30.
Okay. He says it's 4K, but he doesn't know the exact field of view. But
Sure.
It's a DJI.
Yeah, the thing that I would just kind of mention, like sometimes sport cameras have, like GoPros and things like that have very wide optics, and so they can gather more things. And obviously you're subdividing that area into how many ever pixels that you have, usually 3800 by 2200 or whatever you got there. But when you're planning that, I thought there were some interesting comments there. You generally have very small number of pixels to fit these targets into. And even though that you're doing some, the 1 foot targets and you're having some, reasonable success, but, by limiting the field of view, I think that you could get at least the, depending if it's the vertical or the horizontal field of view, also like that idea about, orienting the camera so that you could see more of your flight path, and then you can look at that a little bit better. But as far as getting into more of the production camera that you guys were looking at, that's where you may change from, the 120-degree field of view for the lens down to 70 or 50 or something else, depending on what you need. It looks like it's detecting very quickly, right? You don't need a particular lot of time or several frames to be able to do that. That would be just maybe a comment on improving some of the detection. The more pixels you have, the better detection you have. So that's always good.
Yeah, I think the next test flight we do will be using the on-semi camera, so it'll be good to see what range of quality we can get out of that.
Sweet.
Okay, good job.
All right, thank you everybody who came to the software presentation. We're going to move on to the electrical slides now, so I'll just switch over. Feel free to run if you have to. Electrical should be about 30 minutes, so we're going to go through this quickly. Real quick overview, if you weren't here before, my name is Matthew Updike. I'm the captain of the Purdue Aerial Robotics team, and what we do is build an unmanned aircraft from the ground up every single year. But we're not, only focused on the aerospace side of things. We also have large electrical and software components, as you may have just seen. We have a big computer vision, segment to our competition, and then we also have large electrical goals in the form of data transmission over extended ranges, power delivery in a complex high amperage system, and then a few other issues that we'll talk through. So right now we sit right at around 75 members. To give you an idea of the size, that's split between those three sub-teams: electrical, software, and aeromechanical. So the competition is an autonomous competition. So we're taking off on a runway autonomously. We're flying a set number of waypoints. And then we're going to do some obstacle navigation during this. And then we'll move on to the software aspect at the end. To give you guys an idea of where electrical stands, in these competition requirements, I mentioned power delivery and I mentioned the data transmission, but they also focus on autonomy. So autonomy is nested within electrical, and what they're doing is path planning algorithms and working with hardware and firmware to kind of get this autonomous aircraft flying. And then really quickly before I hand it over to Hadi, our electrical lead, here's a quick schematic of how the competition works. So as I mentioned, we take off, we then navigate a set point of GPS coordinates while making sure that we avoid these yellow cylinders, which are no-fly zones. We then drop a target from the aircraft before moving on to our computer vision section. And then we, while doing this computer vision section, we're going to be relaying images back to the ground. That's where our data processing or data transmission comes into play. And then at the end, we land hopefully safely autonomously. So I'm going to hand it over to Hadi now, who is going to be running you through the autonomy, data transmission, and power delivery tasks within the electrical team. And the way that we plan for this to be formatted, we have about half an hour worked out for this presentation, and we'd like for it to be as interactive as possible. So, jut in during the presentation if you have any interjections or any critiques. Please make sure to bring them up right away. That way we can talk through the problems and have a really productive conversation. So here's Hadi.
All right, thank you, Matt. Okay, yeah, good afternoon, everybody. My name is Hadi Ahmed. I am the electrical lead for Purdue Robotics here. And the electrical team at Robotics has three major goals that Matt kind of mentioned earlier: autonomy, data communication, and power delivery. So, well, there we go. The first of our goals is the autonomy, actual flight control part of our teams. So autonomy has four major focuses within autonomy: autonomous path planning, target searching, a UGV drop, and dynamic obstacle avoidance. At this time, we are primarily focusing on the first three, the path planning, target searching, and UGV drop, with the hopes to work on dynamic obstacle avoidance, meaning avoiding other UAVs in the sky that are flying at the same time as us later on in the year, if we have the manpower and resources available to us. So first, we have the actual objective for autonomy, and that is, as the name might suggest, to create an autonomous flight system that will completely take over all control over the aircraft while it's in the air and fly given waypoints through a certain radius, avoid both the static and dynamic obstacles, and find and identify targets that are located on the ground in some unknown location, and also create a high quality map equivalent to a Google map kind of satellite view. So currently for path planning, we are using an A-star algorithm with a Dijkstra heuristic to make sure that we can fly around the waypoints and around obstacles. However, this algorithm is very computationally intensive and not easy to run on the aircraft or even on the ground in a short amount of time. For that reason, we are turning to RRT, or rapidly exploring random trees, where we essentially randomly sample fields of points around the airfield and create a path through those random points to reach our goal in a much more less optimal, but much more computationally intensive, less intensive path. You can see an example here on the big black picture on the right, the big blue circle obstacle, and the actual tree that this created when I'm moving around, not fully optimally like how you might say as a human, but it is very easy to calculate and really easy to actually figure out if it's correct or not, compared to something like A-star, which requires many iterations and significant amount of computational overhead. One also consideration is that A-star does not allow us to consider turn dynamics, flight dynamics, just turn speed, turn angles, stall speed, stuff like that, that RRT star allows us to take advantage of. Further, we can then trim and prune these waypoints created by the RRT algorithm using either Dubin's curves or polynomial curves, giving us a flight plan that is guaranteed to be flyable and efficient enough for our use cases. We are looking for the best to do what works. Next is our survey pattern. So like I mentioned, there are going to be targets located at unknown locations on the airfield. And all we are given is a general area of where we can search within. And we obviously also know our flight dynamics, like our turn speed and our bank angle. And we must then figure out how can we create a path that will cover all parts of the airfield and take a picture of at least one picture of every part of the field below it. So right now, here's a current implementation. As you can see, is not ideal, as there is a small strip of land between the 0, the big circle in the bottom there, and the tiny little yellow circle 07 is not being covered by our current flight plan. Our hope is to try to figure out how to adjust for this and make sure that we are avoiding obstacles that could be in the actual search grid, while also making sure we're actually covering all parts of the search grid. The hope is that if we can do like a flyover of the entire field before we're doing our search grid pattern, you don't have to do a random kind of searching pattern, rather can focus our searching on targets that we know might be in a certain location. For example, by the 04 or by the B2 waypoints, instead of figure them out over the entire airfield. And finally, to kind of make it all work, we're using the ROS, or Robot OS, to connect our PX4 flight firmware to our flight computer using the Maverick communication protocol. This allows us to mix Python and C++ for both fast prototyping and efficient code delivery at the very end, and on the ground allows us to pre-generate waypoints using a much more powerful computer, and then upload the waypoints to the actual PX4 firmware using MavROS, like the latitude, longitude, and altitude of each waypoint. And finally, when we're ready to take off, we can use the PX4 mission mode to launch our mission and automatically take off, fly waypoints, and then land. The hope is then to also use this MavROS implementation to add dynamic flight avoidance, since we can drop in and out of mission mode using PX4 and using the MavROS in the onboard flight computer and make split-second decisions about how to turn to avoid other in-air aircraft. Second is communications. So communications has three main focuses: radio hardware, the transport software, and the antenna tracker to make it all work together. So obviously, because we're taking so many images on board the aircraft, it is not fully possible for us to process them all on board our flight computer. And as such, we must transmit them down to the ground for either further processing or submission to the judges. And as a result, we must get a system that can autonomously send them and track the UAV from several hundred meters away, since we cannot be guaranteed where the UAV will be in relation to our location at any given point on the actual competition day. And so to do this, we have some criteria and some limitations here. First, we have to make sure it is fully autonomous, meaning no human can either initiate or accept the transfer of data to or from the aircraft. Second, we want to make sure we're covering a complete semi-sphere around the entire airfield. So that's complete visibility around the horizon horizontally and complete vertical visibility as well. This ideally should work up to 1 kilometer, but I don't believe the airfield is more than a few hundred meters, so I don't think that we need to hit the whole kilometer. And finally, we would like to make sure we're reaching at least speeds of 30 to 300 megabits per second. Since any slower, and there's a possibility that we are not going to be sending data back fast enough for software to process or for us to submit. To aid in this goal, we've decided to use 5 gigahertz Wi-Fi in comparison to several other options we consider, like FPV drone systems or 2.4 gigahertz Wi-Fi. We chose this because 2.4 gigahertz Wi-Fi, while it has a higher range than 5 gigahertz Wi-Fi, significantly lowers the bandwidth capabilities we can send over compared to 5 gigahertz Wi-Fi. And so to use this system, we're using 2 Ubiquiti bullets, one for the ground and one for the UAS, along with one Omni antenna for the aircraft and a 30 dBi grid antenna for the actual ground station. We chose the Ubiquiti bullet product for 2 reasons. One, they're easy to come by, easy to configure, which makes our team's workload a lot lower. And second, the power requirement to turn on and sufficiently power the radios is very low. Most radios that we found used a 48 volt PoE or power over Ethernet standard. However, the Ubiquiti bullets only use 24 volts. And since our flight batteries are 22 to 24 volts at any given time, it means that we can actually power the bullets compared to some other possible radios that we could choose. And the Omni antenna for the aircraft is simply because we can't track our ground station accurately from the aircraft at this time. So an Omni antenna allows us to broadcast a signal and use a much more powerful antenna on the ground to make sure we are honed in to make the actual link line of sight perfect. On top of this radio hardware, we plan to use gRPC and the protobuf library, which is an open source library maintained by Google. Thank you for that. Maintained by Google to actually send data between the aircraft and the actual sky. So for that, we're using gRPC because it has high speed over the HTTP protocol. It allows multiple languages, so we can use both Python, again, for prototyping and C++ for speed. And it has a streaming focused mindset, meaning we can just send data back and forth, and we are guaranteed to make sure that it'll always be transmitting and always be utilizing the full bandwidth. For that, on the actual ground, we'll be using a Python-based client that has a low, we don't care about efficiency too much, we can use Python here, but on the sky, we'll be using a C++ server, since C++ compiles to be much more efficient and much faster than Python. We can then send requests to our server in the sky and receive responses as the server is able to actually implement them. And finally, to make it all work, we plan to use an antenna tracker. So as I mentioned, we have an omnidirectional antenna on the aircraft and a directional antenna on the ground. However, the directional antenna has a very low narrow beam width, about 12 degrees, I believe, if I remember correctly, meaning we have to make sure that the plane is right in the middle of our beam width for us to actually have a connection to the aircraft. For that reason, we plan to build an antenna tracker out of a tripod, some servo motors, and a flight controller, the GPS receiver, to make sure we can calculate where the antenna tracker is in relation to the aircraft and pan and tilt itself to make sure it is lined up to have line of sight with the aircraft at all times. At larger distances, it's less of a concern because 12 degrees is a pretty big cone after several hundred meters. But the main issue is if we are within 100 meters of the aircraft, the actual 12-degree cone will be very narrow, meaning we have to make sure our GPS receivers are very accurate so we can actually pinpoint where the aircraft is, since a few degrees off could mean the difference between no and full connection. And finally, we have power delivery. So power delivery has 2 focuses, battery sizing and voltage scaling. So our objective is to basically fulfill every power requirement on board the aircraft. That includes 2 motors, a flight controller, a flight computer, radio hardware, and a bunch of other things. It's a lot of things going on here. And we have to power these for a full 25 minutes for the competition. The big catch here being several, if not all of these components, have different voltage and different current requirements, meaning we must scale and adapt our system to match the needs of anything downstream from our batteries. To do this, we have broken up our electronics into 2 systems, propulsion and avionics. Propulsion will consist of 2 batteries solely focused on powering the 2 motors and ESCs, while avionics will be a much smaller battery solely focused on powering our autonomy computer, our flight controller, our image processing radios, and flight controller. This allows us to kind of have multiple different voltages going on and allows us to expand our capacity in a much more dynamic way. Since if we need more flight time, we can add a new flight battery. And if we need to save weight, we can cut down on our avionics battery without hurting performance anywhere else. So for battery sizing, we have a main issue where we have 2 motors that draw a lot of current, about 80 amps possibly in one instantaneous draw. If we were to use a single battery, that would mean we have like 10 minutes of flight time, which is not ideal for our situation. So for that reason, we have to calculate what is the capacity we would need to reach 25 minutes. And assuming we know how much throttle we need and how much current it will draw from the motor, can we calculate that from, you know, a reverse formula? And so to do that, we decided to test our motor in a real life setting by attaching it to a static test stand and measuring the current going through the wires as we go through different throttle levels, and then create a physical model showing throttle and time over currents, as you can see an example of on the graph right here. As you can see, as we increase the throttle over time, the current increased somewhat linearly, but not perfectly. And this allows us to model at any given thrust requirement that Aeromet gives us, we can predict what the current draw will be for the motor at that time. Then using a theoretical battery model here, the flight time formula you see underneath the screen, we can then reverse calculate how much the battery capacity would need, knowing flight time, discharge, and our average amp draw overall. And finally, voltage scaling. So the two major needs here are the Pixhawk flight controller needs 5 volts at 2 amps off of our 22 amp battery, and the NVIDIA Xavier NX needs 19 volts at 2 amps, which is a very unusual voltage scaling. And so a custom chip must be designed to convert our 24 to 22 volts to 19 volts. The big concern here is both chip and battery protection, since a voltage spike or a current spike in either the battery or the NVIDIA Xavier could cause damage to either or both actually the chips. And second, the high chip frequency, about 1400 megahertz, introduces many parasitic resistances and capacitances to our circuit that can cause our actual voltage and current response time to be delayed, meaning there could be damage to the chip and to the circuit if we cannot provide the requested current in a smooth enough amount of time. With that, are there any questions about our implementation or things we can clarify to everybody here?
Matthew, this is Russell. I just have a question on your wireless system. Have you done any testing on that yet? Or is this all, have you done any like preliminary testing? I know you said the specs say it goes from 30 to 300 megabits per second. And I'm just curious, you know, you got to be aware a lot of times the actual throughput you'll receive from these systems is not always as advertised. So I was just curious what kind of testing you've done on the ground and or in the air.
Yeah, for that, Duncan here, who's our lead, can talk about that in more detail.
Yeah, so those values are actually what we calculate from the tested values. At most, we got around 300 megabits, around, I said around 10 meters. And then as we got further, the lowest is around 40. So it's like we've done a lot of testing, but we haven't had a lot of land or ground, like somewhere with clear point of sight to test up to 1 kilometer. So we estimated that 1 kilometer is probably our max range right now. And we're planning on doing more testing next semester. So.
Okay, excellent. And just to clarify, was that ground testing, like where somebody had an antenna on a pole or something, or was that actually airborne flight?
It was on the ground.
Okay. So yeah, well, that's great to know. I definitely highly recommend doing some flight testing as well. And then also you might find some issues and change the antenna placement as well. So great, thank you.
Thank you for that. Yes.
Back on the slide where you were talking about how you tested the motor, current draw.
Yeah, 1 second, sorry, yeah.
I believe you said you're looking to provide enough power for the average draw.
Yes.
What happens if you're flying in extra windy or gusty conditions? Then we expect the power draw to be more than average.
Yes, that is correct. So our current goal here is to find the average draw, then account for worse than that. So we have to hope for average draw here just because we can't account for every possible variable that could increase current draw. However, we do know the absolute minimum thrust that the plane must create to fly. And so using that, because we know current and throttle, and we know thrust and throttle, we can then kind of figure out current to thrust. And then with that, we can kind of make a plot of current over thrust or thrust over current, and then find a value that way instead. Yeah, but our plan right now is just do an average, like, hopeful best case scenario. But once we have more time to test, we fully plan, and Aeromet kind of finishes their designing, we can actually figure out what the throttle needs to be and then account for that instead, and kind of set up like a best average case.
Yeah, along those same lines, so generally, with a current draw like that, you generate constant torque, not necessarily a constant speed. So if you think about it, a really common example with older cars, when you switch from the recycle to the external air, you'll get a change actually like with the controllers weren't in a constant speed. So that's just something to think about that with your draw here to figure out how much, the windy conditions. I don't know how you could bench that, but coming up with that, trying to figure out what that constant speed needs to be in order to generate, whatever thrust that you need. The other thing that I had a quick question about was the power supply chip that you had. You had a buck converter there. Yeah. And so, this particular chip has 14 megahertz. I'm sorry. So that's probably 1400 kilohertz is what I'm guessing, not 1400 megahertz, because that'd be 1.4 gigahertz, right? Switching speed.
The frequency of the NVIDIA Xavier.
So I'm sorry, what was that? I didn't hear that.
Yeah, I believe that's the frequency there is for the NVIDIA Xavier. That's the actual clock cycle for the NVIDIA Xavier, not the.
Oh, okay, got it. And do you know what the switching speed for the buck converter is?
Ethan, what was that again?
And that would be dependent on the internal MOSFETs of the design, which it's probably on the data sheet, but off the top of my head, I'm not sure what the switching frequency of those MOSFETs would be.
Yeah, not 100% sure right now at the moment, but some data sheet somewhere.
Sure, no problem. One thing that I would consider, so a lot of newer chips, you're trying to get to like a 2 megahertz switching speed, or some of them have 3 megahertz switching speed. You have a lot of switching loss when that's when you're operating like that. You have a lot of current that you're operating with. So I would recommend going slower. Maybe a 300 or 400 kilohertz. It's a little bit easier to compensate for. What ends up happening is your inductor gets larger because you're trying to filter out the ripple, and you need to make sure that your inductor can handle that without saturating. But it also gives you better efficiency generally because you're not switching so fast. So there's this trade-off between miniaturization of components, right, with 2 megahertz versus maybe less switches in a particular time and better efficiency. So obviously that plays into the weight and how much power that you're having to put through that. But maybe take a look at that.
For sure. Thank you so much. You definitely will.
Sure.
Any other comments or questions about our designs?
Do you have a separate system for your ground vehicle drop? I may have missed that when you showed the chart.
Yeah, so at the moment, we don't have a battery for that just yet because we don't have any dimensions for that figured out yet either right now. So we don't intend that that will be a separate battery system. However, that's still very much to be determined.
Okay. I guess my big comments are that I almost wonder if you ought to have a separate team for autonomy versus electrical power, because electrical power is such an important part of this aircraft design. Was just a thought. The other thought was you have 2 batteries powering the 2 engines. Are you equilibrating power from each of those batteries before it goes to the engines?
Could you clarify what you mean by that?
So if I just hook up one battery to one engine and a second battery to a second engine, I'm going to get varying power outputs for any given throttle setting. And so I'm wondering how you're going to equilibrate those engine to engine, side to side.
Yeah, so our current plan is to put them in parallel so we can maintain the same voltage across both cells, but have increased capacity. The one concern with that is because LiPo batteries are very difficult to work with. If one of the cells drops below the voltage of the other cell, it'll be reverse charge, which could be a hazard. However, since we are getting new batteries and make sure we balance charge them the day of, and every flight test we do with these batteries, I don't think that'll be a major concern for our team.
Okay. The other thing is, I mean, when you're using the twin engines, you're going to get, I mean, even with a single engine, you're going to get some vibration through the vehicle. And something to think about is how many of these devices and how many of these power sources need to be isolated from that vibration.
Yeah. Yeah, I think we definitely look at, about vibrations a pretty big concern for our team. I know for sure the camera will be, as Matt said, on 2 different stabilizers. And we might want to put the computing devices on one as well, because that could damage some of the silicon there as well. But I do believe the airframe can probably handle a little bit of vibration.
Yeah, well, I don't think the airframe's the issue. I think it's the attachment of the various components to the airframe that'll be your issue.
Absolutely.
I guess I had one last comment, and that's for Matthew. Matthew, when you make this presentation next time, I would like to see your overall mission profile devolved into a set of mission requirements.
Okay.
And then a mission or a requirements tree down to the various subgroups, so that there are requirements for each of them that tie back to the overall requirements, and have a way to show us what those look like and how well you're progressing toward meeting the overall mission goals.
Yeah, I think it's very important. We've done that somewhat internally, but we didn't showcase it. I think you do bring up a good point that, especially for the audience, it's something that's pretty important to showcase. So we'll definitely, consider that next time.
I mean, each group spoke around it, but they didn't really show them.
Yeah.
Okay.
Concrete numbers or specifications. So yeah, I agree. Could have done a better job on that. Okay. Does anybody else have any last minute questions? Otherwise, we're going to wrap up here.
I know I've mentioned this before, but I sent you guys the paper that I've been telling you about. So that's in the chat, if just so everybody saw that. But for the autonomy group, that's kind of the best of both worlds for RRT and A-Star kind of run together. And they've done a lot of experimental work, and those guys are working at Skydio now. So it's pretty practical. I think it's a good paper. So check it out.
Yeah, we're actually, that's a MIT CSAIL aggressive flight one, right?
What was that?
That's the MIT aggressive flight CSAIL one.
It's the one where they put a LiDAR in front of on a fixed wing with a twin engine fixed wing and float in a parking garage.
I think that's actually the paper we were referencing while we're doing our design. So we're definitely keeping in touch with that.
Okay.
Sweet. All right. I think we're just about at our time. So, unless there are any last minute questions or red flags, from these 3 presentations that anybody wants to outline, I think we're going to go ahead and close it out. I want to say thank you again. We really much appreciate all of your guys' time and effort. Do you have lost link procedures? Hadi, do you want to talk?
Yeah.
Hadi, talk about that quickly.
Yes. So by lost link, I assume if you lose line of sight with the aircraft. No, if you lose our intent tracker line of sight with the aircraft. So yeah, that is a concern for our team. We don't have any ideas for that at the moment. So I'd love to hear your thoughts about what we could do to implement that, in our software or hardware.
So yeah, so lost link is one of the most critical safety features that you definitely want to implement and test to make sure that works. Because with the weight of that aircraft, like there's definitely a danger of that thing, actually hurting somebody. So what I would recommend is whatever your flight computer is if you do go lost link, or if the link degrades to a point where it's not getting command correctly, to have some sort of fleet plan route, or just bring it home. because what you don't want to do is just have that thing either waste your time, your flight time, doing routes that you've already programmed in. You want that thing to get back into your link so you can get control of it again. So there's definitely more than one way to do it. There's more than one right way. But I would definitely make that a high priority item, just, for safety especially.
For sure, yeah. We actually do have two fail safes, actually three fail safes in our team. One for if we lose manual control, one if we lose telemetry, one if we lose actual Wi-Fi, 2.5 gigahertz Wi-Fi. So I think right now our plan is to kind of return to home if that happens, but we might look at other options as well. Yeah.
Sounds good. Thank you.
Great. And I see you linked a paper there, Professor Gopper. Okay.
Oh yeah, that's just the parameter to set that lets you determine if you lose comlink, what happens on the PX4 autopilot.
Okay, cool. Awesome. All right. Well, like I said, we're at our time. So once again, thanks to all of you guys for coming, virtually and in person. We really appreciate this. I'm going to go ahead and send out an email later tonight. And I'll include a kind of, a way for you guys to provide additional feedback if there are any questions that we weren't able to get to. I know we were a bit pressed on time. We could have had, 6 hours and I still have been talking, but I really appreciate, focusing in on some of these potential problems. And we'll be in contact in the near future about that. So yeah, that's pretty much it. And so, yeah, I'll send that email out, and otherwise, class is dismissed. Thank you so much.
Yeah, great job.
Bye-bye.